everyone. It's our first time we are doing a hybrid. And so well, it's our honor to be the first time to do a hybrid with Giuseppe. But I'm going to stop here and I'll invite Martin Walter, who is the section head for the CIBM Niche, to give an introduction on Giuseppe Iacobucci, our speaker today. Thank you.
Thank you very much, Pina. It is my honor, it's my absolute pleasure to introduce to you, dear colleagues, dear friends, Giuseppe Iacobucci, Pepe Iacobucci. I have to say I've been doing research for 25 years now in the field of nuclear medicine. I've worked with a lot of smart people, and I've worked with one person that I consider a genius, and that person is standing in front of you and will give the talk to you today. So Pepe Iacobucci, he graduated from University of Bologna with a perfect score, 110 of 110, summa cum laude. And he is at the University of Geneva since April 2011. We're very, very excited to have him here. Since 2014 on, he was director of the Department of Nuclear and Corpuscular Physics at the University of Geneva. And from July 2020 on, the president of the physics section of the University of Geneva. Next to the many, many important roles that he played and that he took responsibility for at the university, he also took over key responsibilities at CERN. For example, in managing and coordinating and having a key role in managing and coordinating the CERN Atlas project. And he did this since 2005, so for quite a while. Since 2018, he is also a member of the PHASER collaboration, a new initiative, or more a newer initiative at CERN. Pepe has key roles at the physics department at the university and in parallel at CERN, which is highly admirable. He has mentored numerous PhD students, numerous PhDs. He received a wealth of research grants, and I looked him up at Scopus today with an H index of 120. He is one of the most cited researchers worldwide. So he has a wealth of academic achievements. And one of these academic achievements is centered around the development of monolithic silicon pixel sensors, and this will be the topic today. So he established this type of research. So basically, got all the research funding, generated all the research funding to build an ultra clean room, and to equip this room to build these sensors. So he started this type of research and needed to build the infrastructure for it and create it himself. So with these monolithic silicon pixel sensors, there were two main directions. One is to create very radiation tolerant sensors, mainly for the Atlas project at CERN. This might be a topic today, but it's not the focus. And the other one is to build very high resolution sensors, time resolution, spatial resolution sensors. And these sensors can be used for PET imaging technology. And this is where the link then came in with medical imaging and the collaboration with Pepe that I'm thrilled about, that I'm absolutely excited about. So on the personal note, I have to say, next to being an awesome researcher, Pepe is a great colleague to work with, and he's a great lecturer that we can learn a lot from. So with this, I'm happy to give the stage to you, Pepe. We're very happy to have you in this lecture series, and we're excited to listen to your talk on your pixel detectors.
Thank you very much, Martin. You are too generous to me, evidently.
I'm just
Thank you. Okay, I'm very glad to be here in this CIBM because I wanted to visit the center since a long time, since more than a year, but of course it was not possible because of the COVID. And then I forced Pina a little bit to do this in a hybrid way because I wanted to meet the people. I wanted to come here and visit the center. So it's my great pleasure to give this seminar today here. And I will tell you, as Martin already explained, about a project that Martin and Michael Unser and myself have been granted by SNF. So the idea is to pioneer ultra-high resolution molecular imaging with silicon pixel detector, monolithic pixel detector. This I will explain you in a moment what does it mean in detail. So this project we call the 100 micro PET, because this is the goal we want to have. We want to have resolution much below 1 millimeter. Now, ultra-high resolution molecular imaging, this is going to be very challenging, as you will see, because the hardware is going to be very challenging. The reconstruction, the image reconstruction software that the group of Michael Unser will produce will be very challenging because he will have to deal with something like 10 to the 15 line of responses. It's going to be very hard as well. The measurements that in the lab, in this lab, Martin will have to do of arteries, of mices that will get atherosclerosis will be also very challenging. So, and this is all work that we have to do. So what I will do today, I will tell you what we have done so far with another synergy project. I changed slide in the meanwhile. And I will explain you, details of the hardware in particular. Okay? So the slide changed. Very good. So what is positron emission tomography? You know it much better than me. This is, you inject a radionuclide in a body. You inject a radionuclide that makes beta plus nuclear decays. That means that it emits positrons, the antiparticle of an electron. So this positron will have a little energy, will move a little bit in the tissue, and then more or less after 100 microns, they will lose all the energy. They will be essentially at rest. They will find the antiparticle of this positron, that are the electrons. They will annihilate, and they will create two photons back to back, always with the same energy, 511 kilo electron volt. Okay? So these two photons back to back, as you see in the figure, will fire detectors that will be more or less opposite in your PET scanner. Okay, and they will determine, they will create what we call a line of response, which is the direction of two photons. Okay, we do not know, in principle, where the annihilation happened. It could be anywhere along this line of response. So what I like to discuss is not really the line of response, but the line of response volume, because this will be given by the length, of course, and by the area of the detectors. So the larger this area, the more is this volume big, the worse will be the contrast of your image, and also the resolution, both of them. So, change slide. So the images on the PET are reconstructed by the projections of the line of response. Okay, so this is how it works. You take all the line of response that go in one direction, you make a projection, okay, then you change this direction, you make all the projections, you sum, you superimpose all of them, and you see the image. You can see there is a darker spot there. Like this, it's easy to understand, easy to look at and say, yes, there is a spot there. But if you have many spots that you want to image, of course, everything will be very complicated. Everything will be very complicated. There are several factors that contribute to the volume of the line of response, and I will concentrate on three of them. First of all is the detector spatial resolution. So these are movies. I don't know if you can see them. Let's see. Let's see. Yes. So in this case, what you see rotating on the left, I'm sorry about the latency of the network. I don't know what to do with it. But however, the idea that I had in making these movies is you see on the left, two sources, each of them emitting two line of responses in red. And then the second source that emits the two line of responses that are in blue. Okay? If the granularity of your detector, the size of your detector is large, you will not only see where they cross, but they will also cross somewhere else. And even if you rotate them, if you take all the projection in space, they will cross somewhere else, most probably, which means that you will have a lot of ghost images, a lot of artifacts. Okay, and there is not much you can do with it. On the other hand, if your line of response is thin as a hair, 100 microns, then if they do not touch, you will see this. And they will touch only in the points where the emission happened. So this is the first thing, to have a very high resolution. Second thing is what we call the depth of interaction. In the PET scanners that we have today, we have crystals that have a certain height, typically a couple of a centimeter, 2 centimeters. And in this case, of course, if your annihilation is at the center of the volume, then your line of response will be dictated by the area, orthogonal area of your sensor. But in the other case, as you see in the left figure here, if your annihilation is not at the center of the detector, then your line of response volume will increase. It will be dictated by the depth of your crystals, of your detector. So you will have images that will have a resolution that will depend on the radius with respect to the center. Okay? So this is not an interesting thing. This is another reason why, if you would have a multi-layer of detectors and you could identify the depth within a certain volume at which the photon is detected, as you see here on the right, okay, you will improve your resolution for annihilation that are not at the center of the scanner. Third thing that everybody knows is the time of flight. Time of flight does the same thing. Okay? You measure the arrival time on the top and on the bottom detector. You to the difference, because of this difference in time of flight, you know with a certain precision where the annihilation happens along the line of response of the two photons. This is another way to restrict the volume of the line of response. So as you see, these three factors, completely different from each other, they contribute to reducing the volume of the line of response. What we want to do, if you want to have a very precise PET scanner with the highest possible contrast also. Now, this is the situation today. This is a compilation from a PhD thesis of 5 years ago. This is the situation today of the volumetric spatial resolution in millimeter cube with respect to the scanner sensitivity, the efficiency in percent. And you see, I mean, where are all the small animal scanners? Okay? Now, my question is there the time? Is this the time for a change of paradigm? Can we do something that is drastically different from what is done so far? Okay? Of course, PET scanners work very well. Since 40 years, they evolved a lot. They are much, much better than before. But the method is always the same. If you want, these are crystals. Okay? That the photon arrives, you have scintillation light, you measure that. You can do a lot with it. But is it possible to conceive a scanner that is completely different and performing much, much better? That would mean to me to have much improved spatial resolution, DOI resolution, and time resolution. So we want to use all these three factors. So, voila, on the left, you see what happens in a normal PET scanner, okay? And you see the dimensions. The depth of the crystal is of the order of 1 to 2 centimeters. The area of the crystals are of the order of a few millimeters per side. Okay? Which means that this is the resolution you can have from this. You can improve it somehow a little bit with time of flight, but not too much. Now, suppose that we can do something completely different. We can do a multi-layer detector. And we do it with silicon detector. They could be 100 micron thick, few hundred micron thick. They will have a pixel pitch, so the area of the pixels could be 100 microns times 100 microns. So you see, you improve in all directions. All these three parameters will improve a lot. So this is the idea that is beyond this scanner that we want to realize. Okay? So I changed the slide, but I don't see it on the screen. Here it is. Okay, so this is the idea, as you see here on the left. Okay, you have a photon that will traverse a multi-layer of, let's say, 60 silicon detectors with a pixeling of 100 microns, extremely precise in the transversal plane, extremely precise in the longitudinal direction of the photon. So the depth of interaction we can measure very, very well. And this scanner should not suffer worst resolution on the sides when you are away from the center of the scanner. No, this is the limit of DOI measurement. Now, what are these pixel sensors? I want to tell you very quickly, what pixel sensors are. As you see in the figure on the left, yes, the figure is there, we use them a lot in particle physics to do detectors, to do extremely precise detectors. You have an image there of the strip detector of Atlas, of the Atlas experiment. But they're using the hospitals to do X-ray imaging now. This is you do not have photographic images anymore. Everything is done with silicon pixel detectors. You use them with your mobile phone. They are inside any camera and mobile phone. Before CCDs were used, which were this kind of detectors. Now we use CMOS pixel detectors, exactly what we are going to discuss today. So there are essentially two types of them. The first one, sorry, there are animations here, but it doesn't matter. We do it without animation. What do we call a hybrid silicon detector? What is an hybrid silicon detector? This is done by three parts. It is done by the sensor that is here on the top. I hope that people can see me indicating on the screen. So charged particles traverses the sensor. It will ionize the atoms. So you will have electrons and holes that will migrate, will generate a signal. Then on the bottom, you have the readout chip. You have an ASIC, a chip with all the electronics for each of the channels. But then you have to connect the two. And you do this with a process that we call bump bonding. You see a picture down here. We put very small balls of metals, 50 microns, 20 microns balls, spheres of metals at a distance of 50 microns. That is the pitch of our pixels. And this makes the electrical connection. But of course, this costs a lot of money, as I indicated on there, because you have 40% of it is the cost of the sensor, 20% is the cost of the electronics of the readout chip, and you have this bump bonding processing, this coupling of the sensor to the electronics is extremely expensive. And also, you want to produce this kind of pixel detectors, you have three production steps. So you have to control each of these steps, that all the channels works and so on. So you need a lot of manpower. It costs a lot of money. On the other hand, and here I'm sorry that the animation will not work like this. On the other hand, look at the right. suppose that we are able to produce everything on one silicon wafer, the same wafer that we use normally for the readout electronics. Suppose that we can install where we have the electronics, also the sensor in the same wafer, okay? Then you save a lot of money because you pay only 20% of it. You do not have 3 steps to control with a lot of manpower that you have to pay to make these controls. This is what we call the monolithic silicon pixel sensor. So it costs less, much less control to be done, but of course there is a caveat. It's very difficult to produce technologically because you have to manage to have a sensor that has high voltage working together with the electronics. You have to isolate the electronics, so technically, from the design point of view, it's quite hard to do this. Okay, this is one. Okay, so in Geneva, there is a tradition that I found there when I arrived 10 years ago in Geneva, a tradition with silicon detectors. There was already a very nice clean room with equipment 10 years ago. So when I arrived to Geneva, I knew nothing about silicon detectors. I said, this is very nice. This is going in my new department. I do not want to cancel everything that has been done for 15 years before me. I want to continue that. So I continued the tradition in Geneva, but I wanted to innovate a lot. So as soon as I felt confident, I started R&D projects on monolithic, because before only hybrids, where monolithic did not exist. Okay, so with other colleagues, we started to discuss on this. So the aim of the R&D that I launched in Geneva 6 years ago was, first of all, to develop and produce monolithic pixel detectors, but in particular, to try to achieve a time resolution well below 1 nanosecond. So the chips, the monolithic pixel that we use in ADRAS and CMS, the delicious experiment, they have a resolution of, let's say, 5 nanoseconds. Okay, I said, no, we should get 50 times better than that, at least. So my goal was 100 picoseconds. As I will show you, we managed to do much better than that. So with this in mind, I mean, we launched the first Synergia project that was SNF Synergia between us, HUG, and University of Bern. The colleagues were Michele Weber from Bern and Osman Ratib from the HUG, that I'm sure several of you know. This was the team at the time. Now, I do not want to show you too many things, but I want to go a bit more in detail on how this scanner will look. Okay? So I'm sorry, I want another slide. Here it is. So on the left, you see the basic photon detector unit. What is that? That will be a layer of an absorber, a converter, 50 microns of lead or bismuth, but most probably be lead. So the photons that are created by the annihilation, okay, they would enter into this layer of 50 microns of lead, and they would convert, this is a photoelectric effect, in an electron. So the electron will come out and will be detected by the monolithic pixel sensor that will be behind it. So this is the idea. We convert and we measure right after that. So as you see, the thickness of a photon detector unit could be of the order of 200 microns. So in 2 centimeters of the volume, if you want, of the normal scanner, we can put 100 of them, many of them. So very high precision measurement in all directions, in the 3 spatial directions. This is the idea. Then, of course, the problem comes because this is not easy to realize technically. Nobody ever made something like this, to glue one on top of the other silicon sensors, make it work. It's complicated. So we squeezed our brains, and the idea was to create what we call a super module. That means, as you see here on the right, a stack of 5 of these photon detector units. We stagger them one with respect to the other so that we can wire bond, we can connect them with very high precision. And these 5 that we call a super module will be on a board that I indicated in green there. where there will be all the connections, all the signals will be driven out of the detector. Then out of this supermodule with 5 detection layers, okay, we will make, as you will see in a moment, yes, on the left, we will create a tower with 12 of these supermodules. That means in total, the tower will have 60 layers of silicon. This to increase the efficiency, okay? This is the old design that we had. You see, of course, silicon, it's like a little lamp. It will warm up because there is a lot of power going into measuring all the electronics that controls all these pixels. So what happens is that we have to cool it. So we need a cooling block that will be on the side. You see there in light blue. Then what we do, these are wedges. We make 16 of them. We put them all around the small animal. And you see on the right what we want to achieve. This is the idea of the scanner. Now, the performance of this. I'm still talking about the old Synergia project, not the one that we have now active with Martin and Michael. Huh? This is the old Synergia project that I'm illustrating to you because the principle more or less is the same. So the performance of that, we have simulated our scanner that we call the thin time-of-flight PET scanner or TT PET scanner. We simulated it and the phantoms in Giant 4 that allows a very detailed multi-particle physics we call a full simulation of the processes and the detector. And we have studied the sensitivity, the coincidence rate, the spatial resolution, the background contamination, okay, according to the NEMA standards. And I want to show very briefly this to you. So first of all, new slide. First of all, is the sensitivity. Here it is. So at the center of the scanner, according to the NEMA prescriptions, we measure 4% sensitivity, which is not bad. This is limited by the fact that we have 6 layers. If we will put 100 layers, we will have more, of course, and so on. And it's also limited by these cooling blocks that are in the inactive material, so they create regions where we are unable to measure. Second thing, we measure the noise equivalent count rate, okay? And as you see, I mean, our scanner is here, is the black here. See, we can run up to activities of 100 megabecquerel or more at a rate of more than a megahertz. So the best small animal scanner that we know about is the Hyperon 2D, and you see here how it performs. So it will be much, much better than this. Why this? Because silicon sensors are very fast. Our electronics, our readout electronics is very fast. So this is why we can really work at very high rate, very high activity with high efficiency. Then we made the reconstruction. You see on the left, the truth, the Monte Carlo truth, simulated the Renzo phantom. Note the rod diameters. We go here down to 0.5 millimeter. Typically, the smaller rods that you see in the Renzo phantom are 2 millimeters, typically, in some cases 1 millimeter. Here it's 0.5. So we made a first reconstruction, non-iterative filter back projection, and you see that without the time of flight information and with the time of flight information, we see enough. We see essentially all the structures, also 0.5. But as you know, filter back projection is non-iterative. It creates artifacts that you see here at the center of these images. So we were not happy. And with Emanuele Piccini, who is now working here at PFL, and Daiki Ayakawa, my PhD student, we set up, but they did set up an iterative algorithm. So, and indeed, as you see, all these artifacts disappear, which is very nice, as expected, but as we increase the number of iterations, we had high frequency noise, as you can see here in the third plot after 100 iterations. So we learned that we are not expert of this. Michael and his group are, so we went through a slow process, slow learning process. We learned that we had to use regularization, the BSOSL method, and you see on the right, everything fixed in the maps algorithm with regularization. Now, in this table, you see the results for the point spread function. I mean, you see several very interesting things. You see that the resolution of full width of maximum in millimeter in the radial, tangential, and axial direction, they are essentially of half millimeter, which is great, which is already very good. It's already a big jump with respect to what is achieved by normal scanners, by conventional scanners. And the other thing that you should notice is that when you move away from the center of the scanner, you see X position 0, 5, 10, 15 millimeters, it does not change. That is exactly what I told you is the virtue of very precise depth of interaction. Right? So we have many layers, you can measure very well depth of interaction. So our resolution does not degrade when we move away from the center of the scanner, as we wanted. Giovanni Frisoni is writing on the screen. Good morning, Giovanni.
Apologies.
Okay, where is now in the diagram that I showed you before, the volumetric spatial resolution versus the sensitivity, our scanner? It is here. As you see, we have 4% sensitivity, but we have a volumetric resolution that is already 5-6 times better than the best small animal PET scanner, conventional scanner. So this is already very satisfactory. So see that people continue to write on the screen. Okay, so we made all the engineering. I think I'm late, so I will go very quickly on the engineering. So we made all the engineering of the scanner. We tested everything. I just show you the image. You see, we made a test of this staggering wire bonding. I'm not sure you can see here, but there are the wire bonds here on this test sample here on the right. And then we made the prototype chip. The prototype chip had 3 matrix of 3 times 10 pixels with a pitch of 500 microns. We decided not to go with very small pixels because of power. The more pixels you have, the more amplifiers you need, the more power you need. We had a budget of 300 watts for the entire scanner, so we had to stop at this size. Why this? Because we wanted to exploit time of flight. We can, our electronic we developed in Geneva is very, very fast, so we can run a detector at 30 picoseconds time resolution. We wanted to use this. But in order to do so, if you want a very high time resolution, you also need a lot of power, which means that you cannot allow yourself too small pixels, because it would be too many channels. Okay? Now, results that we got out of this. We make tests at the test beam at CERN and in our lab. As you can see from the screen, I mean, we have full efficiency. They are essentially 100% efficient. And we were very happy about this. Also, if you look at the resolution, the time resolution, we measured 114 picoseconds for minimum ionizing particles. That means that in the case of 511 keV photons that are in the PET scanner, that you want to measure in the PET scanner, you will have electrons that you convert out this photon that will have at that energy will produce much higher ionization. There's about a factor of 4. So the goal was achieved. Okay? So we were very happy about this. So this was then the basis of the second Synergia project that we launched and we got approved, Martin, Michael, and myself. Okay? So we used all this. We have demonstrated we can do it. Then we sent this second funding request to SNF, in which we show that we can do better than this. We can do much better than this. I will show you why. Because what we realized is that if we give up the 30 picosecond time resolution, I go directly to the results that I want to show you. So if we say, okay, we don't want to measure with 30 picoseconds time resolution, but we measure with 200 picoseconds, that is already quite fast, okay? Our electronics will consume much less power. So instead of having these large pixels that you see here on the bottom left, we can make pixels of 100 microns. Would it be an advantage to be so precise? I mean, at the beginning we were thinking, well, but we know that the mean free path of the positron in the tissue will compromise this. We said, well, yes and no. It depends on the type of radionuclide that you use. If you use oxygen 15, for example, the full width half maximum of the mean free path of the positron in the tissue is half a millimeter. But if you take FDG, it's 100 microns. So it makes sense, because if you want to use FDG, and as you know, 95% of the exams in hospitals are done with FDG, it makes sense because it is the mean free path of the electrons is very short. So it makes sense to make this very precise detector. So our idea now has been, the proposal to SNF has been the following. So let's drop the idea to make a time of flight scanner, okay? On the other hand, let's point everything on the spatial resolution so that our line of response are very thin, 100 microns, few hundred microns, like an air. This should help us very much in having high precision, okay, and in having the highest possible contrast, because we will have less accidental ghost superpositions of these line of responses. So does it work? Well, we made a calculation, of course, with that you find here on the right for pixels. Oh, this is what you see here on the left is what I've already shown you. It's with the old scanner with 30 picosecond, 500 micron pixels. I mean, what you see here on the right is what we obtained with a simple filtered back projection with pixels of 100 microns each. As you see, we can reduce the full width of maximum of the point spread function to half of what we had before. So it works. And when I showed this to Michael, he told me, oh, we'll do much better than this, I'm sure, because this is just a filtered back projection. And this is why we decided to call the new project 100 micron PET, because we aim at doing better than the 300 microns that you see there, resolution. Which means, and I changed the slide, looking back again to, I'm sorry, but here it is. Looking back again to this plot, this compilation of small animal PET scanners, volumetric spatial resolution as a function of the sensitivity. This is where our old project was, but if we make 100 micron pixels, giving up the time of flight measurement, as I showed you, as I told you, this is where we will be. We will have the same sensitivity, but much better volumetric resolution. So this is now more than one order of magnitude better in the volumetric spatial resolution. And SNF liked that, and they funded our second Synergy project. So with Ashuje, Martin, EPFL, Michael Unser, and me at the University of Geneva. We started the project in July, the 1st of July, because of the COVID and the hiring. The slide with the team will appear. Here it is, the team. I mean, we hired Mateusz, Jihad, Pablo, Xiaoying, Alix, ACR in the three departments. Okay, we started on the 1st of July. So we just started. So all the work is to be done. The work on the hardware, the work on the reconstruction, the work that Martin will do in in his department. So we made 4 work packages. The first one is virtual animal, is to build this ultra-high resolution PET scanner. Sorry, this is the construction. The PET is the first one. The second, we introduce, I mean, this is very interesting because the idea is to make a virtual ultra-high resolution mouse via autoradiography, okay, and then digitize that. Then, of course, the project of image reconstruction by the group of Michael, and this will be, as I said, very challenging because there will be 10 to 15 line of response. So, but Michael, Paul, and the group, they have already many ideas that we discussed. And then, of course, at the end, the molecular imaging, the measurement that we will do on the APOE mice at the Hôpital Cantonal in Geneva. Now, the timeline will appear in a second. Voila. I gave emphasis to 2 milestones. The third one is the delivery of the hardware and the software. That means that at the end of Q1 2024, we need to have the scanner ready and all the software ready. At that point, we will commission it still for some time at the University of Geneva. Then we will move it to the HUG, where it will be commissioned with the phantoms, and then the group of Martin will start the measurement with the mice. So 2024 is the most important milestone. So again, this I do not want to show, yeah. But since then, if I have time, do I? No problem, I take my time, okay. Because this is the project that we submitted to SNF and was approved, so we should be already very happy. But given the fact that we did not start the project immediately, we have been continuing to thinking, to brainstorming, and we had a lot of new ideas how to improve the scanner even further. So the design that I showed you has a problem. Well, in reality, it has 2 problems. First of all, is that the cooling blocks that are needed to keep the controlled temperature of the silicon, otherwise, as I said, it's like a lamp, will somehow chauffer. We need these cooling blocks, but as you see, they are in the sensitive volume of the scanner. So this creates an inefficiency. And in PET scanners, inefficiency is a big problem because you need to detect 2 photons. So if you have, they occupy about 1/4 of the volume. If you have an inefficiency of 1/4, so you have 75% inefficiency, this is for 1 photon, but you have to measure 2 photons. It means that you have to multiply these 2 inefficiency. You have to do 75% times 75% will be the efficiency of the scanner. So the efficiency of this design will be 56% of what could be, or what is the full efficiency. Okay, so we would lose more or less half of the pair of photons. This is why, and also, I mean, the head of my engineering, mechanical engineering group tells me, this is a nightmare. We can do it, but it's very difficult because with wedges, in reality, they are this thick, they are this long. Okay, you have to make 16 with very high precision. I mean, you put 15 one after the other, you mount around, then the last will be very hard to make it fit because we have really to work at the 10 micron level on a big system. It's not easy at all. So also to cope with this possible construction challenge, I mean, we devised a completely different design. I mean, the way in which we work in the CERN experiments, we take a silicon pixel chip detector and we make quad modules. We take 4 of them. We wire bond and we serve them with connections for the signals and high voltage. We create quad modules. So I said, why don't we do the same here? We are already developing that for Atlas and for FASA, for 2 CERN experiments. Let's do the same. So the idea now is instead of the 16 wedge-shaped blocks, to have 4 bricks. 1, 2, 3, 4. Okay? And the nice thing with it is that, as you see, these are now the cooling blocks. Now the cooling blocks will be outside the scanner. Okay, they will not be inside the volume. So this will be much more efficient. This is what we call fully active. This is the first thing. So we should gain quite a lot in efficiency because with this new design, that is also easier to achieve from the mechanical point of view. Two advantages. Second thing was the following. So on the left, you see the sensors the kind of sensor that we use, for example, the LHC, and that I intended to use for the PET scanner, the 100 PET scanner. So you have two kinds of processes that allow you to detect the photons. The photoelectric effect in LED, in which the photon kicks out an electron. This is the photoelectric effect discovered by Einstein. He got Nobel Prize not for the relativity, but for the photoelectric, or maybe the Brownian motion, I believe. But anyway, one of the important three discoveries of Einstein in 1905. Then the second one are the Compton effects that are especially in the silicon. Okay, so this is what we do. But now, I said, yeah, but if we look at the relative amount of efficiency that comes from the photoelectric in the LED, in the converter, in the absorber, and the Compton that happens in the silicon, in the 50 microns depleted silicon, that is the active region of the silicon, you see that we have 21% efficiency from the photoelectric and only 3% coming from the Compton interactions in the silicon. So I said, but why we need to work only with 50 micron silicon? Let's work with 250. This we can do, changing the resistivity of our silicon wafers. And I mean, we will be in a situation like the one you see here on the right, with 250 microns of active silicon layer. This means that the amount of photoelectric effect will not change, will continue to be 21%, okay, efficiency for these photons. But the Compton now, we will have 5 times more the silicon. They will move from 3% to 16%. So as you see, we can increase a lot the efficiency for the detection of one photon. That means, again, we have to measure 2, so you have to square this. The effect is enormous, and I will show you the level of the effect. Okay, this is another thing I will tell you afterwards. This you see now, this is the 100 PET that we proposed to SNF, but if we change the design from the 16 wedges to the 4 bricks, the fully active design that I told you, we could increase the sensitivity from the initial 4% to 6%, but up to 14%. And this is incredible. You see, we have a 1 order of magnitude more or less in all directions. So if we manage to do this, this will be really outstanding scanner. I mean, these 6 months of brainstorming were very useful, I have to say, for the project. So an advantage of the COVID crisis. Okay, another thing I want to tell you is that I like very much this Compton, that normally are the enemy in PET scanner, because Compton are the scatter inside the volume, what we call scatter. They destroy your resolution. But these are Compton in the silicon, so they will be very precise because they are in the silicon. The photons are not deviated. They do not create bad resolution, this Compton here. This is fine for us. Okay? They are even better than the photoelectric. So what you see here is the resolution in millimeter. So you have a photon that does, for example, a Compton here, okay, or photoelectric, and then you have the electron that goes out of this Compton event or photoelectric event with a certain angle. So what is the error that we make in the position, in the measurement of the position? So how much is this delta X? Okay, so look at the plot here. Look at the plot here. These are 100 microns, these are 200 microns. So most of them will be within 200 microns. So very precise. Okay, here the mean free path of the positron in the body is not considered. So we have to add that. That will be another 100 microns to put a quadrature inside. But as you see, this will be extremely precise. And if we look at this plot in log scale, but you already see it here, I mean, you can see that no absorber means the Compton. The Compton have a tail in the distribution of the resolution that is smaller. So they are more precise intrinsically. Okay? So everything seems to go in the direction that we need to, I want to show you this again, that maybe we have, it's a deal if you want. It's a deal between a lot of resolution. Here, as you see, this goes up, goes from the same value of the volumetric spatial resolution up, this symbol. So you could have 6% sensitivity, but even better resolution. Or you can have a much larger sensitivity with a bit degraded resolution. With respect to resolution, this is already an order of magnitude better that you can achieve today, of course. So this will be up to the group of Michael and up to the group of Martin, together, of course, with us, to determine which direction we want to go. So this will be a matter of study in the near future. Now, I can stop here. I can move forward. I move forward because there is something more I want to tell you. Where are we? I mean, with the silicon sensor, the monolithic pixel silicon sensor that we are preparing for the 100 moped. Okay, so you see here the articles and also 2 patents that my group made on this subject. So this is my team at the University of Geneva, and my main research partners and funding agencies that I want to show you. These are the prototypes. Next slide. Yeah, we made many prototypes, as we see, and this is the one that we are testing now that we want to study for the 100 moped. And I will show you the results that, that we measured at the CERN test beam. First of all, if we run our electronics at full power, we obtain 38 picoseconds time resolution, which is really excellent. This for sensors of this type, without what we call a gain layer, I will explain this to you in a moment. I mean, the best was about 150 picoseconds. We managed to have better than 40, which is great. And then efficiency, we have a 99.9% efficiency. So they are fully efficient. I don't go into the details of this, too complicated, but this is the main point. 99.9% efficiency, 38 picoseconds. So the chip seems to work very well. I'm delighted about this. Now, last thing, then I will swear I will stop. But so the 100 moped scanner is already a supercar, as you see. But why not dream of speed? I mean, Mercedes wins also in Formula One. Huh? Why not add the time of flight again? Can we do that? We already do 38 picoseconds. Can we do even better than that? Well, here I have an ERC project that I call the Monolithic that is exactly to do that, to implement a gain layer. I don't go into the details. I mean, to implement a gain layer in our sensors to increase the time resolution. To what? I show you what the simulation told us and convinced the ERC panel to fund this research project. I mean, we could have sensors that go up to 2 picoseconds. So I would foresee in the future that, I mean, if everything is fine, with 100 moped and we achieve this incredible PET scanner of new generation with silicon, we could also have a second step in which we include also the timing, which will make the life of Paul, Michael, and the others much easier, because if you have also timing at this level, you have 3D points that you have to put in the space will be much easier to reconstruct. So I think I stop here because it was already too long, maybe, I'm afraid. Thank you very much for your attention.
Pepe, thank you so much for this. Thank you so much for this excellent talk. I'm involved in the project, and I again learned something. So thank you very much. I have one question. If in the audience there is a researcher that does not work with PET, but works with, let's say, CT, who also uses detectors, is there good news for those researchers too on the long run, do you think?
I believe, well, at the moment, I mean, the detector that are used in CT are already very good, they perform very well. The only thing that could be added is timing.
Okay.
So there was a study recently that showed that if you have a timing to time of flight measurement with the precision of 10 picoseconds, you can reduce you can improve the contrast of images. Okay, so this is interesting because you see, the photons that go through the bones, for example, they do not go, or the tissue, they do not go straight. They are scattered, they deviate a little bit. So deviation means longer path. So the time of arrival will be longer. So you can use 10 picoseconds time resolution at minimum, okay, in order to do this, to improve the contrast of images. Okay, but it's not at all easy to achieve a 10 picosecond time resolution.
Understood. Okay.
10 picoseconds, I mean, the light will travel for 3 millimeters, which is
fast.
Yes.
So dear colleagues, dear friends, the paper, the presentation is now open for discussions. Are there questions from the panel in the room? Are there questions from the panel in the Zoom?
Maybe, may I start? Thank you very much. It was a very, very nice talk and we learned a lot. And it's very impressive to see how we can scale from a huge detector to small animal imaging. Now, to go back to human PET system, how do you see the translation from your approach for animal to human?
Okay, thank you for the question, which is very interesting indeed. Now, why we concentrate on small animal PET scanners? Because as I have shown you, to have a sensitivity of 4%, we need, or 6%, we need to have 60 layers. Okay. Now, a small animal PET scanner would mean already several million channels of electronics. Because of this multi-layer, you need 60 layers. Okay. So this kind of scanner, I judge that it's very hard to scale to human or even to head scanner, because it would be too much silicon. On the other hand, there are other possibilities. Instead of using a silicon detector, we could use other detectors that are more keen to stop the photons, like cadmium telluride, cadmium zinc telluride, and this start to be studied. With these kind of detectors, we could reduce by a factor 3 or 4 the number of layers. So we could do it with 15, 20 layers, let's say, okay? Which means that we can make a larger scanner. But of course, there are technical problems there, because you cannot do that monolithic. You need to have separate chip of electronics and sensor. Now, it becomes technical, sorry, but this is the essence of it. Do you want to bond them? No, absolutely not. I do not want to do that because it's very expensive, it's very complicated. Companies have to do it, and companies do not want to do this because it's not a commercial procedure. On the other hand, we are developing together with several people, the CERN, also the Medipix people. Geneva is part of the Medipix, TimePix collaboration. We are developing a way of gluing them, We call this method ACF. This is glued with little spheres of let's say 30 microns or so. And we should be able at a certain point to glue this the chip to cadmium telluride sensor, for example. This will allow to produce a head scanner, for example. Sorry for the long answer, but it's technical. I had to explain it.
Okay, thank you. And I don't know if I can go on, but in the past, when the PET MRI came into the market, people claim that putting the PET camera inside a strong magnetic field would increase the resolution. Do you have any comments about this?
Well, in the sense that you will have the two images and you get the structural from the MRI and the functional from the PET. In this sense, I mean,
no, I think it was more like the free pass running by the
because of the magnetic field.
By the positron, yes, was shorter.
Could be a bit better. On the other hand, I mean, the first Synergia project, the one with Bern and with Osman Ratib, the idea in 2016 was indeed to make a PET scanner that could go inside an MRI. This is why it has this cylindrical layout also. But it's not easy at all. If I see all the work that my friend Craig Levin had to do, I mean, it's not easy to put a lot of material inside the huge, the very large magnetic field on MRI and very variable with time magnetic field. So it's not easy. On the other hand, I mean, suppose that you have a PET scanner that has 300 micron resolution. I think it can run by itself. Yep. It will be a level of precision of the images for which, I mean, you do not need to work together with an MRI. And indeed, for the second Synergia project, we abandoned completely the idea to put this scanner inside an MRI because the resolution we are having now is even better than what we had before. So we are really trying to create a different object, a PET with an ultra high resolution for molecular imaging. Okay. We have to hope that we will manage in the 3 years that come.
So thank you very much, Francois. Are there other questions from the panel or from the Zoom?
Any questions in the audience?
There was one question in the comments section, if I may read it. So it's not at all my expertise. So please excuse if I mispronounce. So it says, "Thank you very much." It's from Somaye Sagamanesh. "Thanks for this interesting talk. Could you please compare the photon conversion efficiency between this silicon pixel detector and current LASO, GSO, and sodium iodine crystals for a given specific activity?"
Yeah, I think the answer is here. The answer is in the horizontal scale of this plot. This is exactly it. This is the sensitivity, so the efficiency that you get with crystals, with the crystals are used so far. You see they vary a lot from 0.1% to 10%, a bit more than 10%. Okay? What we can do with the old design is 4%, so it sits here somehow in the middle of this bunch of PET scanners. Notice that we have a log scale, so this is logarithmic scale. Okay, but with the new design, okay, and increasing the silicon, the active silicon from 50 microns to 250 microns, we can get up here. So as you see, I mean, we can do better than the best small animal PET scanner done with crystals. Of course, I'm not giving you the number, per photon, I'm looking at the system answering to you.
Okay. Okay. Well, thank you to the colleague for this interesting question. Thank you, Pepe, for answering the questions. Are there other questions?
Yes, Bernard?
Do I have to talk in a microphone? Or
No, it's fine.
Okay, very good. Well, I had actually a question about, so sooner or later, when you push the spatial resolution of the reconstruction you're building with your extremely nice sensors, sooner or later you reach the physical limits of the positron annihilation itself. So the free diffusion of the positron, but then also the non-collinearity of the photons which are emitted, which is more of a problem for human scanners than small animal scanners.
Yeah.
So at some point, the intrinsic spatial resolution will be limited by that phenomenon. I was wondering whether actually another advantage of your extremely sensitive sensors, especially for human application, could be that you could run PET scanners with much lower doses, injected doses to the patients, because the invasiveness of the PET is still limited by the dose applied to the patient, which is, well, which does not allow to make a PET scan every week, for example. So do you think
Scanner?
you could not run a PET scan on someone every week? But I mean, would that be another approach or another selling point for the technology?
So there are many questions there, one at a time. What's the first question?
So the question would be that since, well, at some point you cannot fight the spatial resolution much further than the intrinsic positron.
Yes. But this, yeah, to this, I mean, I can show you the table. Let me see a little bit where it is. This table here. Okay. What you see on the left is what we obtained from a full simulation that includes also the mean free path of the positron in the tissue. Okay, with 100 micron pixels. Reconstructed, we went through full reconstruction, but with filter back projection. And you see that we achieved already 300 microns. Okay, so with a very simple reconstruction, okay, we can get to 300 microns. So this answers your first question, which is when you get to the limit that comes from the mean free path of the positrons in the body. So you see, 300 we can do with a trivial reconstruction. Then, as I said, Michael and his group certainly will do better than this. Okay, so this is the first. The second question, if I remember correctly, you said, I mean, in a human scanner, you have a lot of material. The body is big, so you have the Compton effects in the body, what are called the scatters.
Well, that's one thing I meant, and also the fact that the photons are not necessarily exactly at 180 degrees, because there is still a bit of kinetic energy.
Yeah. But this is, I mean, this is part of the art of bioimages. I mean, of course, there will be a reconstruction, code, filtering. I mean, probably very complicated that will take care of all this. I mean, this is part of it. This is part of the game.
I don't see it as a negative point. I just think that
I understand.
Since you have pushed the detection to the best, would it be useful then to be able to decrease the dose you need for a PET scanner?
I mean, this is something that might happen. Again, it depends on the contrast. It depends. Now we are moving from linear responses that are more or less, I don't want to say like fingers, but like a quarter of a finger. Okay, and we have to use all the costs that they create and the problem that they create to the contrast of the images. We are moving with this scanner to linear response volumes that are as thin as air. So it's from the point of view of the reconstruction, there is a lot to be understood, because there also, I mean, as Michael and Paul will tell you, it's completely new system. It's completely different paradigm. So as we are, and we have in the past, and also over the last 6 months, you see, we have been brainstorming a lot and having new ideas that seem to be very interesting. Will be the same with the reconstruction. As soon as we will produce, we have to produce in the project the simulated annihilation to them. We are not yet done it, so it's not their fault, it's our fault. We have been a bit slow there. I'm sure that when they will have the giant event, the simulation of the events with the scan and all the material, I'm sure they will do amazing things.
Very impressive. Thank you very much.
Thank you for the question.
Thank you very much for this excellent question. Are there other questions for paper?
If there are no other questions, I would like to thank Professor Giuseppe Iacobucci for this wonderful talk and to offer him our
thank you very much.
CIBM gift, and also our annual report. If it's part of the news, it's out. I mentioned it many times before. So please go onto our website and download it if you want to know everything about 2020. 2021 is almost over, and then we'll have the 2021 report soon.
Thank you.
And thank you very much again.
Thank you very much. Thank you for the invitation, for being here.